At first, I would like to thank David for giving this opportunity to me to present my presentation. Today, I will talk about the linear scaling coupled cluster methods. And our linear scaling methods are based on the molecular fragmentation. So far, various molecular fragmentation approaches have been suggested to overcome the stiff scaling problem of electronic structure methods. In MF approach, a molecular system is broken up into small molecular units and energies of the fragments are combined to approximate the energy of the entire system. Although logic behind the whole fragmentation approach is similar, the formation of fragments and the combination of the fragment energies differ significantly from method to method. And in terms of accuracy and general applicability, the systematic molecular fragmentation approach appears to be very attractive. In SMF method, we start with a molecule M and we divide it into different groups. Groups are the set of atoms defined by the SMF algorithm. The basic ideas involved in the method can be illustrated for the simplest case involving a chain-like molecule containing N groups connected by single bonds. For example, this is our molecule, which includes the N groups. The target is to derive an accurate value for the total electronic energy, which is a function of groups. And the energy of the molecule M is determined by the summation of the fragments, which are defined in terms of the combination of groups. The size of fragments depend on the level of SMF, and the fragments can overlap with each other since a group can involve in multiple fragments. Therefore, additional fragments with negative coefficients are generated to cancel the effects of multiple counting. And SMF energy consists of two components, the abundant energy and non-abundant energy. And abundant energy can be expressed by this formula. In here, Fi is the integer coefficient associated with the fragment Fi. For a model system of chain containing 5 groups, let's say pentan molecule, the SMF fragmentation scheme can be expressed as this. In here, each G represents a methyl group. So at level 1, we are just combining 2 groups. At level 2, we are combining 3 groups. And at level 3, we are combining 4 groups when we are fragmentizing the molecules. And all fragments with the negative coefficients are just added for the purpose of chemical balance and to avoid the multiple counting. Thus, the fragment sizes increase with the level used. However, number of fragments grows linearly with the system size. And since the abundant energy only includes the nearby interactions, one should consider the non-abundant interactions between more distant groups. The non-abundant interactions may be evaluated by this formula. In here, Fi and Fj's are the coefficients of the fragments capitalized Fi and Fj. And where allowed means that non-abundant interactions that are not already included in the abundant energy formula. And for a chain like alkyl molecule, for example, the SMF scheme, the number of abundant and non-abundant fragments can be given by these formulas. And in case of a chain like alkanes, and if we apply the level 3, which is the minimum level, with it we can obtain a good chemical accuracy. In this case, fragments are just the butan and propan fragments, and their numbers scale linearly with the number of groups. And exact number of non-abundant fragments scales quadratically. So it doesn't matter if you increase the level to go to level 4, 5, etc. Of course, the running equations are a little bit different, but one thing is not changing. The number of abundant fragments scales linearly and number of non-abundant fragments scales quadratically with the system size. However, if we would like to obtain a linear scaling approach, we may consider only short-range non-abundant fragments. Their number also scales linearly with the system size. Therefore, we introduce a non-abundant cutoff tolerance, let's say delta NB. So if the distance between the closest atoms of 2 groups is larger than delta NB, then this non-abundant fragment is disregarded. Now I would like to show you some results. We have implemented a systematic molecular fragmentation approach code, and we have integrated it with our DF-OCC module. And in here, we run several calculations with more than 100 molecules. As I remember, it is 142. So we consider all isomers of these molecules, and we run the calculations with the canonical methods. For example, in here, the error of LS SMF CCST parenthesis T is compared with the canonical CCST T. Therefore, we use a relatively small basis set because we need to compute the entire molecular system. And comparing with the canonical method, we observe tolerable errors in considered methods. For example, for the CCSDT, it was lower than 1 kcal per mole, but for the Hartree-Fock, we obtain larger errors. So it appears that fragmentation approaches are promising, at least for the test case presented. Then we further investigate the effect of basis sets. We employed a larger base set, but in this case, we cannot proceed with the canonical CCST parenthesis T, even with the DF version. Therefore, we have used the FNO CCST parenthesis T. And as we increase the basis sets, we observe a slight increase in the mean absolute errors, but still all errors appears to be tolerable for the Alkan set. Next, we consider higher levels. If we are not satisfied with the level 3 fragmentation, I think initially I was thinking that level 3 will be enough, but when we get more experience with the molecular fragmentation, now we think that one must apply level 4 and level 5 at least for the high accuracy results. And if we applied level 4 fragmentation or level 5 fragmentation, we observed a significant reduction in the errors. However, in this case, since we have the larger fragments, again, we consider the FNO CCST parenthesis T instead of the canonical CCST T. Then in this slide, we assess the performance of our new fragmentation code. So how fast we can fragmentize the molecules. And in here, our code reads the molecular geometry information and then form the all groups and then forms all non-bonded fragments and form all bonded fragments and then write them to the files, preparing the Cypher input files. So all these tests are performed in very short times. For example, for an Alkan molecule with more than 50,000 atoms, the fragmentation code prepares all inputs for Cypher just in 8 minutes in our computer. In here, I also would like to show you some results to get some understanding about how fast this fragmentation approach and how promising this approach. For example, for this molecule, it includes more than 10,000 atoms. This is a linear Alkan. If you would like to calculate its energy with CCST parenthesis T with at CC PVTZ level, there will be more than 190,000 basis functions. So by using the level 3 fragmentation and integrating the LSSMF with the canonical CCST parenthesis T with the DF version, and we run this energy computation on our Linux cluster, which includes the 100 nodes and 4 cores are provided to each node. And the whole energy computation is performed just in 24 hours. So considering how large the molecule and how many basis functions would be in a canonical computation, we conclude that the fragmentation approach appears to be very promising. Of course, it doesn't mean that there are no problems with this approach, but presently we are, and of course some other groups are working on this, and we are trying to obtain more and more accurate fragmentation approach, and we know that its efficiency already quite remarkable. And what else we are doing lately? I also implement a library of molecular integrals and their first derivatives for densely fitted methods. So I have the all basic integrals and three index metrics and their metric integrals and their first derivatives. I can build the form matrix and compute the analytic gradient with Molint. It is not more efficient than Libint, but quite close to the performance of the Libint. Okay. And I also completed the frozen natural orbitals for the UHF reference. In Cypher, we already have one in the FNOCC module and another one in the DF-OCC, but now we have the UHF version as well. Further, we have recently implemented unrestricted DF-CCD and CCSD energy and analytic gradients. And additionally, we have implemented the energy and analytic gradients of the DF-OCCD method. In here, OCCD stands for the orbital optimized coupled cluster. All RHF and UHF versions are available. And we also completed a UHF DF-CCSD parentheses the energy code, which is also completed and works nicely comparing to the canonical code. And finally, I would like to note that we are presently working on the UHF DF-CCSD parentheses the analytic gradients code, collaborating with David, and several of my graduate students, Yavuz Alagöz and Aslı Ünal, are helping me on this implementation. So finally, I would like to thank the TÜBİTAK, which is our financial sponsor, and Betül Ermiş for her contribution in the systematic molecular fragmentation code. She is also one of my graduate students. So finally, I would like to thank you for paying attention.